In the nitration reaction, you are substituting the hydrogen on the benzene with the nitronium group. So your electrophile in this case is going to be the nitronium ion. And to make the nitronium ion, you are going to react nitric acid with sulfuric acid. And that is going to be the first step of the reaction to make the electrophile. So you're going to start with the nitric acid and the sulfuric acid. Draw both Lewis structures. After you draw both Lewis structures, one of them is going to be the acid and the other one is going to be a base. Now we know that both of these are acids, but you cannot react them as acids because if you react two acids together, there will be no reaction. So one of them is going to be more acidic than the other. And it's the hydrogen that is connected to the oxygen and the sulfur that is going to be more acidic than the hydrogen that is connected to the oxygen and the nitrogen. This is why the hydrogen from the sulfuric acid will behave as an acid, and sulfuric acid will be our acid in this case. So the nitric acid now is going to behave as a base. And to behave as a base, we're going to use the oxygen now, not the hydrogen, the oxygen. Our target is to free the NO2 because, after all, we are making the NO2 electrophile. Our target is to free the NO2 in there because we are making the nitronium ion. To do this, we need to get rid of the OH. OH is a bad leaving group, so we have to protonate it. So this is why we're doing an acid-base reaction. The first step is going to be from the base to the acid. Base always takes the acidic hydrogen. You are going to make water, and then water will be kicked out by resonance. So you're going to do resonance in there, water will be kicked out, and you're going to make the nitronium ion. This is the Lewis structure of the nitronium ion, and this is going to be the electrophile. During the process of making the nitronium ion electrophile, you are generating two conjugate bases, the HSO4 negative, the sulfonate base, and the water. Sulfonate is going to be a stronger base than water because it does have a negative charge, but you can use either one of those bases in the third step of the electrophilic aromatic substitution reaction. Now, after we made our electrophile in there, we react it with the benzene by doing a nucleophile electrophile reaction. Benzene will break its aromaticity, open up, picking up the electrophile in there. You are going to form a resonance stabilized intermediate. That intermediate is a non-aromatic intermediate. It's less stable than the product. So you take one of these intermediates and you react it with the conjugate base that is formed in the solution to regain the aromaticity back of the ring. Whether you use the hydrogen sulfate or you use water as a base, both are going to come and take the hydrogen to restore the aromaticity of the ring, and you are going to create your nitrobenzene product. Plus, you're going to regenerate your catalyst back. It is very important when you introduce a group on the benzene to know what group is that. Is it an electron donating or is it an electron withdrawing group? So in our case in here, you have a benzene with a nitro group on it. To know what type of a group is this, you have to draw its Lewis structure. And the Lewis structure for the nitro is this, where the oxygen is a negative charge. It's making one bond. And the nitrogen is making over here four bonds in there. So that is going to be a plus charge. The total charge of the structure is going to be 0. By definition, we know that benzene is electron rich. Okay? However, when I place a group on the benzene that is directly connected to the benzene, and that group has a plus charge on it or partial positive, either or, then that group here, or this nitrogen, okay, that is directly connected to the sp2 hybrid carbon, this one is an electrophile. This one is an electron deficient. So if it is an electron deficient and it's placed next to an electron rich species, what's going to try to do is going to try to steal electrons away from the benzene. Okay, so your electrons now are going to go from the benzene towards the nitrogen just to compensate the loss of electrons over here. That is going to make the nitro group an electron withdrawing group. So this guy over here is going to be an electron withdrawing group. Nitration reaction is very important because in nitration reaction, I can introduce an electron withdrawing group to the benzene. And also, I can change that electron withdrawing group to an electron donating group by doing a simple reduction reaction. So with the reduction reaction, I start with benzene. And on the benzene, I have my nitro group in there. And with the reduction, the definition of reduction, I am replacing the oxygens. This is what reduction means. You replace the oxygens with hydrogens. So now I'm going to end up having an amino group on the benzene rather than a nitro group on the benzene. We said that the name for this structure is aniline. This is nitrobenzene. The reduction reagents to carry the reduction are quite a few over here, and you are responsible for all of them. So any one of those can reduce the NO2 into an NH2. Now, why do I care? I care because NO2, if I draw the Lewis structure for, it has a plus charge. It is an electron withdrawing group. However, with aniline, if you draw the Lewis structure for NH2, you can easily see that the nitrogen in there has lone pairs. When nitrogen has 3 bonds, it has lone pairs. When nitrogen has 4 bonds, it has a positive charge. It makes a difference if the substituent on the benzene is having lone pairs versus a plus charge. If it has a plus charge, then it's an electron withdrawing group. But if it has lone pairs, then it donates electrons to the benzene. It gives electrons by resonance to the benzene. So here you can have electron donation to the benzene by resonance. So that is going to make the NH2 group here an electron donating a group.